All right, welcome everyone. It is 9 a.m., so let's get started. Welcome to the VID's short paper session on personal visualization theory, evaluation, and extended reality. My name is Cindy Zhang. I'll be your chair for this session today. So we have 8 really great talks. I know because I got a sneak peek of them, and 2 of them have won Best Paper Honorable Mention. I will encourage you to take advantage of Discord to interact with the presenters who are here and virtual, and make sure to use Slido to ask your questions. So we're going to start with a presentation from Valencia Bullock to talk to us about exploring design of personalized visualizations.
Hello, my name is Felicia Bullock, and I am currently a second-year PhD student at Stanford University. Today, I'm excited to present the following work on behalf of my co-authors, Let's Get Personal, a paper that explores the design of in-the-wild personalized visualizations. In a world where online news platforms and blogs compete with social media outlets for user engagement, there's a pressing need to generate content that connects with users. Traditionally, online media platforms have relied on feed personalization to engage with users. This form of personalization tailors the type of content and/or the order of content that appears on a user's news feeds. However, some outlets have begun to employ content personalization, or personalization that uses demographic information from users to personalize content. For example, by automatically inferring or asking for the age and location of a user, a news article might show a personalized visualization that segments data based on the user's demographics. Accompanying article text may also be personalized to complement the visualization. In practice, this is known as a personalized visualization. Specifically, we extend Gearing et al.'s prior work to define personalized visualizations as visualizations where users manually or automatically provide personal demographic information, such as location, income, race, and gender, to modify the base set of facts shown in the visualization and/or accompanying text. An in-the-wild example of such a visualization is shown on the left. This visualization from flowing data allows users to modify the base visualization by entering their age and biological sex. However, there are a number of challenges surrounding personalized visualizations. First, it's unclear if visualizations will actually increase user engagement. In particular, journalists in prior work have voiced concerns that asking for certain demographic information may turn users away from the visualizations completely. Furthermore, personalized visualizations raise questions around exploration and impact. Yi et al. Note how important interaction and exploration are to understanding visualizations. However, prior work has found that users tend to underexplore visualizations in comparison to designers' expectations. Will personalized visualizations add to these exploration concerns since users are only seeing a segment of the data? And how will this trickle down to the insights that users generate? Will they be generalizable or will they be biased given the segments of data that users have seen and/or explored? In order to answer these questions, we first need to understand how personalized visualizations are designed. Specifically, how do designers structure personalized visualizations, encourage exploration, and present insights? To answer this question, we developed a corpus of 47 articles within the wild personalized visualizations and conducted a design space analysis. Each article contained at least one personalized visualization that matched our earlier definition. Furthermore, we included articles from traditional news outlets, digital visualization publications, and public-facing research centers. We then used multiple rounds of qualitative coding to code each article across 5 major categories. For this paper, we only described the categories pertinent to our analysis: data properties, guidance, and insights. Through our analysis, we first find that designers underutilize instructions asking for personally relevant data, as well as data notices. For example, despite the title that speaks directly to the user about their server within their state, the visualization from 538 does not include instructions that encourage users to actually enter their own state. Furthermore, majority of the articles in our corpus did not include a data notice indicating how users' information would be handled or stored. This article from the Wall Street Journal was one of the few that contained a clear notice, explaining that information users entered would not be stored or used outside of displaying the visualization. The lack of data notices and instructions further underscores questions about whether or not users will interact with personalized visualizations and how these simple design interventions can play a role. In addition, we found that designers rely on exploration examples rather than suggestions to encourage users to view graph segments that are not personally relevant to them. We define exploration examples as interventions that allow users to see non-personally relevant data values without explicitly telling the users to try specific values. The visualization on the right from the Wall Street Journal showcases a common type of exploration example, default values. Without entering any information, users can see the debt to earnings ratio for adults who obtained a bachelor's degree in business administration from the University of Pennsylvania. However, it's unclear if such indirect examples actually help people to explore more configurations of the visualization. In contrast, some articles included exploration suggestions that aim to explicitly point users towards different configurations of interest. For example, the visualization on the right from Flowing Data includes an exploration suggestion in the text following the visualization. In particular, the text suggests that instead of inputting their own age, users should try moving this age slider to 0 to see the rate of change in mortality as people get older. However, a majority of the articles did not include such suggestions, raising questions about the effectiveness of both exploration examples and suggestions when it comes to increasing user exploration. Finally, we found that while several articles included some type of personalized insight, majority of these articles did not include personalized insights that could be visually seen in the graph. For instance, Reader's COVID-19 vaccination tracker allows users to search for a specific country and view a customized page with text and visualizations about the country's COVID-19 response. While the visualizations show the total number of infections and deaths since last year, the personalized text provides cumulative information since the pandemic began, an insight that cannot be extracted from the visualizations. Given the importance of redundancy in understanding visualizations, not visually complementing takeaways from the text may hinder users' ability to remember and discern important takeaways. With these findings in mind, we outline 3 pathways for future work in hopes of understanding how to effectively design personalized visualizations. First, we recommend that future research should look at whether or not users choose to interact with visualizations and the type of information they're comfortable providing. It is important to note how design mechanisms like instructions and data notices play a role in this. Second, we recommend that future research should investigate how interventions like exploration, examples, and suggestions encourage users to view data configurations that are not personally relevant to them. Finally, we recommend that future work examines users' takeaways from personalized visualizations. Are they generalizable or personalized? What happens when users' personalized insights diverge or align with the author's takeaways? Through these trajectories, we hope to provide better support for designers creating personalized visualizations. Thank you for taking the time to listen to our presentation. If you are interested in learning more, we encourage you to read our paper and reach out if you have any questions. Thank you again for your time.
Thank you for the presentation. So we have a question from Matthew Bremer. The flowing data example embedded the personalization control directly into the chart caption, whereas other place these controls adjacent to the chart and text. Do you expect a difference in reader behavior between these 2 design alternatives, and which do you recommend?
That's a really good question, and we saw this in a couple different places. I can't necessarily speak to like how a wide set of users would be able to interact with that in a general sense, but I can say what happened personally with some people that looked at the visualizations. There were some instances that depending on where the controls were, you just didn't realize you should have been like clicking something. Okay. You didn't know whether or not you should have been clicking something or moving around. And in some cases, particularly in that flowing data example, there was a like sentence or 2 in the first opening paragraph of the article that redirected the user back to the visualization for redundancy. So I think off of that, there's not necessarily a point that I would recommend without some type of empirical research, but that point of redundancy and looking at the fact that if the controls are overlaid onto a visualization, it can be helpful to have that redundancy back in the text so that users don't miss that, because there were a couple instances in a couple articles where it was really easy to miss the fact that you could actually interact with the visualization given how it was laid out.
Thank you for that. Really quickly, a second question. How do you think personalization in visualizations can help people draw insights from data more effectively?
So I think a lot of the prior work in this area, which isn't a ton, but some of the arguments from the prior work is that it can be personalized visualizations inherently make things more personal. So even if a topic is far removed from you or may not be something that you totally interact with on a daily basis, by making something personal to your area, to people that you believe you identify with, be it across race, age, income, if you don't have experience with a topic, it can really help to bring it into full circle without you having to have direct experience. And I think that is really important on a variety of different issues where things might be happening globally or even locally that we may not be aware of. But being able to add that contextualization, even in other fields, is just seen to be as being more effective for people's learning. The question becomes how to do that and to what extent personalization helps with that context.
Thank you so much for your answers. Let's give a round of applause to our speaker one more time. So next we have Mark Kowalski to talk to us about the influence of visualization literacy.
Hello, my name is Mark Satkowski, and I will present our work, Who Benefits from Visualization Adaptations. This is joint work with my colleagues Raimund Daxet from the Interactive Media Lab Dresden, as well as Franziska Kessler and Susanne Narses from the Chair of Psychology of Learning and Instruction at Technische Universität Dresden. Our work was motivated by three core ideas. First, information visualization become more common in our everyday life and more relevant for a growing number of people. Second, at the same time, the data that is presented becomes more complex and growing size. And third, the number as well as variety of available visualization types also increases. Those points result in a situation where it becomes harder to develop as well as maintain expertise in working and understanding specific visualization types. In general, the competence to read, understand, and analyze information visualizations can be subsumed under the term visualization literacy. Different assessment tools have been developed to evaluate this literacy. To counter possible missing competences in form of a low literacy score, adaptations of the visualizations can be used, similar to responsive visualizations. The effect of such adaptations is likely to depend on the used visual features and the literacy level, whereof the latter is also described by the expertise reversal effect. Following this, we hypothesized that an interrelationship between the visualization literacy and the presence or absence of an adaptation exists. A better understanding will allow us to design support with a better person intervention fit. That is, to provide individual users with a visualization presentation that is most beneficial for their performance. To investigate this idea, we conducted a study. Its aim was to better understand if a missing visualization literacy can be countered by, for example, the use of specific visualization techniques, which could be facilitated for visual adaptation approaches in the future. The study was conducted as an online experiment implemented in Lime survey, with an average duration of 50 minutes. We invited our participants through various channels and collected data from 42 participants. Previous studies have demonstrated that visualization literacy can differ based on the type of visualization. To account for that, we used both bar charts and scatter plots for our study. Further, we chose the de-emphasis approach as our adaptation technique, which creates a simple pop-out effect. This leads to a 2x2 factorial design on the factors adaptation and visualization type, resulting in 4 conditions. For the experiment, we created 5 task groups based on a combination of low-level analysis tasks of 4 visualizations, namely filter, as well as computer-derived value and range. The so-created questions were based on a subset of the Gapminder dataset. An example question is, in how many regions is a life expectancy of 2006 above 70 years? In total, we created 20 different tasks, 5 for each condition. The visualization literacy level was also used as an independent variable in our study. Here, we chose the visualization literacy assessment of Boy et al., which allowed us to evaluate the literacy for both visualization types separately. As performance indicators, we calculated task accuracy and task completion time for each task solved. The scoring was dichotomous, scoring 1 in case of correct answer and 0 in case of an incorrect answer. Additionally, the completion time was corrected for outliers. In addition to the performance indicators, we also collected user experience data for each of the 4 conditions. We used the scales dependability, usefulness, and intuitive use of the user experience questionnaire plus. Also, we asked the participants for their preferred visual representation style. For the analysis, we used linear mixed models, as they allow to account for the repeated measures and visualization literacy score interaction. For the dependent variables of performance, we included the factors participants, task groups, and the interaction as random effects into the model. We found a significant effect of the visualization literacy and the adaptation technique independently for both visualization types on the task completion time. We found an interaction effect of literacy and adaptation on bar charts, while no other interaction were found. Furthermore, the task accuracy was only affected by the adaptation for the scatter plots. In contrast, the user experience scales were significantly affected by the adaptation. This effect was greater for scatter plots. Additionally, the use of the emphasis approach was slightly preferred by the participants as seen here. Our results demonstrate an interaction effect of visualization literacy and adaptation technique as hypothesized. However, this effect is only visible on bar charts, but not for scatter plots. We conjecture that there are 3 possible reasons for that finding: the visualization type, the visual style and form of the adaptation, and the visualization literacy in relation to the participant sample set. Taking a closer look at the visualization types reveals that the way the data is encoded differs, which results in varying ink-to-data ratios for both types. This also affects the effectiveness of our chosen de-emphasis approach, as it was only applied to the data objects. With regards to the visualization literacy of our sample set, we can see higher scores and different distribution of scores compared to the original test of Boy et al. This is likely caused by our mostly academic sample set. However, as we found an effect of the visualization literacy, we conjecture that this effect may become more prominent in a sample that is more varied in terms of literacy level. To conclude, our findings suggest that taking individual visualization literacy levels into account may be a promising way to create adaptations tailored to the individual needs. We hope that we can motivate future research projects interested into exploring this relation further. With this talk, we presented our study and findings. For a more in-depth analysis, as well as our hypotheses, please refer to our paper. Additionally, we provided all of our study material as well as the collected data and evaluation scripts with the supplemental material and an appendix PDF, which is also accessible on our project page at imld.de/vl-adaptation-study. And with that, I thank you for listening.
Awesome. Thank you, Mark, for your presentation. We have a couple questions on the Slido. The first one is from Hyuk, Kim from Northwestern. How are other factors like graphical density, representation complexity, among others, that are introduced by adaptation related to visualization literacy?
Thank you for this question. We believe, so with regard to graphical density, wait, let me check the question again. Yes. To visualization literacy. The point is that different types of graphical objects, so the graphical representation of the data objects like lines, bars, or scatter or points, could differ how well people can perceive the objects, which means the ink to data ratio, and therefore also how well an adaptation based on the data objects can change how well an adaptation can be added to the visualization.
Awesome, thank you. Really quickly, one more. Who were the participants in your study and how high was their literacy level?
Yes, the participants we mainly collected through two survey websites, but additionally also to our mailing list of our university. Therefore, they were mostly on the academic side, which means either students, but also completed either a PhD, but also so with a higher education rate. And with regard to the visualization literacy, therefore, I would like to point you to our appendix file where we further detail how high the visualization literacy scores were, but they were relatively high, so above average compared to the work of Boyd et al.
Awesome, thank you. There are a couple more, but we'll just post them on Discord. Let's thank our speaker one more time. And next we have Yuan Ding to talk to us about improving graphical perception through feedback mechanisms. Let's welcome Yuan, our first in-person presentation of the session. Apologize for the delay. It was working when we tested it 30 minutes before the presentation. So we're just gonna have our presenter email the presentation to a different computer that is more liked by this machine. And we'll figure it out. Just use this time to meditate. Thank you for your patience.
Apologize for the delay. Good morning, everyone. My name is Yiren Ding from Worcester Polytechnic Institute. The paper I will present today is Viz Quiz, exploring feedback mechanism to improve people's graphical perception. Okay. So data visualization engineers use different data visual channels to encode the data, build a lot of data visualizations, and the readers retrieve the data values from the charts. And this is called graphical perception. A lot of research has been done on improving the expressiveness of the charts, and a lot of studies has been done on measuring and modeling how well people can retrieve data values from data visualizations. However, not too much research has been done on improving the performance of graphical perception. So graphical perception is a fundamental topic in data visualization research. Probably the most classical one is Cleveland and McGill's graphical perception experiment. The task is quite simple. We show a chart to the people and highlight two components, one smaller and one larger, and we ask the question, so what percentage does a smaller value represent of the larger value? And the answer apparently ranges from 0 to 100. And the result is straightforward too. We care about the error between the two answers and the given answer. Here, the above part is the original result from Cleveland McGill, and the lower part is a replication from Hill and Bostock. Here is probably where we draw the conclusion bar chart has the best performance. So the researchers launched a lot of graphical perception experiments. We collected data and run data analysis and modeling. However, the participants' performance cannot be improved from it because they don't even know their answers are correct or not, and they don't know their answer, how many their answers are off from the true answer. And meanwhile, if you notice, the graphical perception experiment is very like a quiz-style questions. They both have true answers, error rate, and we can basically generate infinite trials. So we have vision that we can use the graphical perception experiment to calibrate people's graphical perception. And we can use the same trials to test it, to measure it, just like how quiz are supposed to work. And all this vision is based on if we can provide proper feedback to the participants. The feedback is work just like a key bridge connecting the experiment and the improvement of people's graphical perception. So the question is, what is the simplest answer and feedbacks we can provide to the participants? We can provide them with the correct answer directly. However, in our pilot study, the text-only feedback showed no difference in people's performance. We need to come up with a better solution. So here I introduce the animation-powered visual per trial feedback. So I used the bar chart here as an example. Two components are highlighted for comparison, one smaller, one larger. After the user input their answers, and the blue dashed zone will show up to visualize their answer in larger components. And the orange zone indicates the true answer, which basically is a smaller component. And the orange zone will move horizontally and eventually overlapping with the dashed blue zone for easy and heuristic comparison. And we also provide the letter grading so the participants can know their performance at a glance. And we also provide a text explanation for numerical details. Let's see some live examples. This example using bubble chart. After participants type in their answers, their answer will be visualized in blue dash zone, and the true answer will highlight on the orange zone and move overlapping with the blue dash zone. Here is another example using pie chart, which has the same concept but a different animation design. So above slides show the per trial feedback. After the participants complete a session of experiments which contains dozens of trials, we will show them a summary feedback page. In this summary feedback page, participants can find out the results at a glance, and they can hover over their letter grade to check the details. And if they click on the letter grade, the animation will be replayed again, and they can check the animation as many times as they can. Here is an example for the stacked bar chart. And the bubble chart and the pie chart we have seen previously. As you can see, we designed different animations for different chart types. So after designing and implementing this feedback mechanism, we launched online crowdsourcing experiment. The experiment has two conditions. Condition one is the participants will receive animation per trial feedback and animation summary feedback. And in condition two, participants will just receive static summary feedback. There are three stages in this experiment. The stage one is called calibration. In stage one, participants in condition one and condition two are the same. They will just receive the static feedback. And in condition two is the feedback stage. Participants in condition one will receive animation per trial feedback and animation summary feedback. And participants in condition two will just have the same settings in stage one. And the third stage is a quiz stage. No feedback will be provided to both conditions. And each participant will be assigned to one condition randomly. Here is the result. This is a confidence interval plot for average response error. As you can see, after participants take our viz quiz, their performance improved. And if we take a closer look, for example, the bar chart, the performance improved even more in our condition one, which is with per trial animation feedback. We also collect the comments from the participants. Most of them give us very positive comments on our animation feedback. And some say it is like rearranging their mind. And Some participants say their strategy of reading charts has been changed, which is very interesting and worth further investigation. For future work, first, we just cover 4 chart types. We can extend this work to more chart types. And second, the Cleveland and McGill experiment are low-level tasks, and we can extend this work to higher-level tasks. And third, the Viz quiz has the potential to become to be used in educational settings, but more empirical study need to be done in the specific settings. That's all of my presentation. Thank you.
Thank you. And for the sake of time, I'm going to skip Q&A for this talk. But
Okay.
please,
Okay.
if you catch him around the conference, ask him questions, okay? And next, we have Vidya Settler from Tableau Research to talk to us about Oscar, semantic-based data binning approach. Let's welcome Vidya.
All right. Good morning. Thanks for the introduction, Cindy. So this is work done with my colleagues at Tableau Research, Michael Carell and Sarah Battersby. So binning is a technique applied to categorize data values or to see distributions of data, and it's often used to reduce continuous data into more manageable categories. Selecting the correct number of bins in a histogram is often portrayed as a trade-off. Too few bins and the distinct shape of the data distribution is lost. And too many bins results in a noisy histogram, making the shape information often difficult to recover. And there are pretty much infinite ways to break up your data, and each of them likely will give a different visual pattern. And the best one often works for the story that you're trying to tell the audience. Take, for instance, these 3 maps showing the percent poverty in the US. And on the left, you see this continuous color ramp where the shades are based on the actual values. So for each county, 2,000 in this case, you might have 2,000 unique shades of colors, which are kind of hard to discern. And in the middle, you have 4 shades determined by equal intervals on the number line. And on the right, you have 4 shades determined by quantiles so that each color approximately has the same number of counties. It's the same data, but as you see here, the pattern might be interpreted quite differently. Bin breaks in their semantics are important for people to reason and understand patterns in their data. And we've all been staring at COVID data, and these 2 COVID maps were released and updated by the CDC. The map on the left reflects new metrics for monitoring COVID, where you can see that most counties are marked as low or medium, indicated by green or yellow colors in the map. And the map on the right reflects COVID transmission rates that shows the majority of the counties have substantial or high transmission as indicated by the orange and red colors. But for someone looking at these maps, they might wonder, what do those green or yellow values really mean? What is deemed as safe? How are these categories broken down? Can I unmask? And while we don't really go into the trust or the ethical aspects of binning in this paper, which are still considered important, our work specifically explores how semantics of known commonly defined attributes, such as age, population, salary, could be used to create meaningful breaks in the data. Most similar to our work is that of Settler and Stone, where the paper automatically generated semantically resonant color palettes like this for a set of vegetables and produce, using a semantic lookup of color names and their corresponding color values. So in this talk, we introduce Oscar, a technique that uses external domain knowledge for recommending semantic bins for numerical attributes such as age, salary, weight, population. And the name Oscar is inspired by one of my favorite Sesame Street characters who embraces his life out of a trash bin. So to generate a lookup of semantic categories, we employ a data-driven approach of mining a public corpus of survey questionnaires out in the internet and publish Tableau visualizations containing bin fields. To create a lookup of bin strings and their associated bin sizes, we use a latent Dirichlet allocation, or LDA model, which is a popular form of statistic topic modeling. So in LDA, documents are represented as a mixture of topics, and a topic is a bunch of words. So for each bin concept, we have a label name and a set of related concepts such as synonyms, along with sets of possible bin breaks. We first take an attribute like passenger underscore age and check if we can compute semantic bins. We apply fuzzy matching and lemmatization to match the attribute to a bin concept, age in this case, that is found in the semantic bin lookup table. And if there's a match, these bins are applied to the attribute to generate a corresponding visualization as shown here. In the absence of semantic bins, like this attribute, number of liters, Oscar then proceeds to part 2 of the process, where it computes default bins by applying some smart defaults to select human legible bins. We constrain the number of bins to a manageable size to avoid too many bins as shown here, and we set the default to 20, similar to that is found in Vega Lite. And we round the bin extents to match the precision of the data, because inappropriate bin precision can be misleading if they suggest precision beyond the precision of the data. We also draw inspiration from Vega Lite's nice operator to round bin extents to appropriate powers of 5 or 10 to avoid arbitrary breaks, as shown here. So we evaluated Oscar's binning algorithm by exploring this high-level question: what are participants' preferences for charts with and without semantic binning? We specifically had 3 hypotheses. The first one was that participants would prefer semantic bins over default bins to better reflect the categories of the attribute. The second hypothesis was that participants would not prefer coarser semantic bins, as it may be hard to discern distribution patterns. And then the third hypothesis was that participants would prefer integer bin starts, as it's easier to understand what these patterns are about. So we recruited 125 participants from Mechanical Turk, and we created 2 sets of ranking stimuli, one using default bins that we just used from Tableau, and the other using Oscar's semantic bins. Participants were presented 10 preference tasks in random order and were asked which chart was most useful for showing the distribution of the data. And here are some key takeaways. So we generally found that participants preferred semantic bins as they felt that they were more natural or familiar with the attribute. Participants preferred fine-grained semantic bins over coarser ones, as the fine-grained ones helped them to see the distribution better. Finally, participants preferred default bins with integer bin starts compared to the non-integer counterparts. The decimals often felt arbitrary and hard to understand. We envision Oscar being employed in visual analysis tools where bins can be recommended for numerical attributes, where clicking on an attribute like fair could create a histogram with meaningful bin breaks, but most importantly, having the opportunity to repair and refine those system defaults. And future work should look at further evaluating Oscar's semantic bin quality for different analytical tasks and user intent. And with that, I'd like to thank you for listening, and here's a link to our paper and our contact information.
Thank you, Vidya, for the presentation. So I have a question from Joe Wood. Did you compare or consider other non-linear binning strategies such as jinx, natural breaks?
Oh yeah, no, we didn't, because we were specifically looking at the semantic qualities of these attributes, and then we just kind of used reasonable defaults for kind of the default ones. But yeah, I mean, it would be interesting to just extend it to some of the other common binning techniques.
Awesome, thank you. There are a couple more, but we'll have to move on. But thank you for the presentation. Let's thank Vidya one more time. All right, and next we have Abdul Rahman Sheikh to share with us systematic design considerations of organizing multiple views.
Hello everyone, my name is Abdul Rahman Sheikh. I'm a PhD student at Northern Illinois University. I welcome you all to my talk towards systematic design considerations of organizing multiple views. The agenda of this presentation starts off with a brief introduction about multiple views and their design challenges. We will then look at previous research and move to the approach of our work where we look at design factors based on perception and content. Following this, we suggest design layouts based on these design factors. We also look at a use case scenario and end with the conclusion. Multiple view visualizations allows users to view and explore data from multiple perspectives or views. MVs are commonly used in visual analysis tools for sense-making of data in domains like multimedia analysis, business intelligence, and cybersecurity. Users often work with multiple views and spatially organize them. Hence, well-designed multiple view systems can improve user navigation and minimize the time taken by a user in analysis. Moving on, why do we believe layouts of MVs are important? Layout of MVs is a key element in designing MV systems. A well-designed system can effectively convey essential information to users by avoiding clutter in the display space. This can improve productivity of experienced or novice users. Current MV systems either use a fixed layout which limits user involvement or a flexible layout which completely delegates organizing MV to users. There is no systematic design consideration of MVs and very less literature on the design of MVs. This leads to the motivation of our work and the design challenge. What important factors should one consider while designing MV layout? In previous related work, researchers such as Chen et al. And Almania and Roberts surveyed the design layout of MV systems and identified a set of different layouts proposed over recent years. However, we argue that a view's content and cross-view data relationship should be key considerations for designing the layout of an MV system. Less research considers the view content or cross-view data relationship in designing the layout of MV system. To address this, we conducted a systematic review of 360 MV designs to explore attributes affecting layout design. We found the typical design for MV layouts focuses on attributes that affect user perception and the content of a view. A user's perception of the view affects their cognitive ability to perform an analysis, and a view's content effectively communicates information through appropriate mediums. We further examine each of these two attributes. Based on perception, we categorize three factors, namely separation, which allows the user to distinguish between two or more views, relative position of a view, and salience, which captures importance of view. Further exploring content, we categorize cross-view data relationship as the sole factor based on content. In cross-view data relationships, content in one view may be updated in response to a user action in another view, or elements may be linked between views, as shown in this figure. The relationship between the content of views provides insightful information and assists users in decision-making process. Based on these two attributes, we suggest 7 perception-driven and 3 content-aware layouts for designers of MV systems. We define perception-driven layouts as layouts that improve visual perception and reduce cognitive load. We then define content-aware layouts as one that focus on views content and the relationship of content between views. Now let's further explore these proposed layouts. The standard layouts adapted widely by most MV systems are flexible layout and fixed layouts. Our third proposed layout, the cascade layout, allows a designer to organize each view in a system into a stack of views known as a cascaded stack. In our fourth layout, called the focus layout, designers can provide a focused window at the center of the display space. In our fifth layout, the split layout, windows can be split so that users can organize different views. In the stacked layout, designers can arrange views on top of one another as they are sequentially displayed in the viewing space. Lastly, evident by its name, the tab layout entirely minimizes views in the form of a tab such that only the name of the view is visible. Moving on to content-aware layouts, we propose 3 content-aware layouts. The first, hierarchical layout. Designers can implement this layout to create a tree-like structure between views with a root view and its leaf views. The design of this layout enables users to keep linked views together and focus on several connections simultaneously. The second layout, composite layout, can provide a system that allows users to utilize as much space as possible by incorporating content into vacant spaces or combining two views. Designers can use the categorize layout to group similar or related views in the MV system. Similarities between the views need to be considered for producing this layout. These proposed layouts can serve as a guiding point for designers of MV systems. In a use case scenario where a MV system has a layout as provided in Figure A, we try to improve the layout by implementing the proposed layouts in this work. The overlap as shown in 5 is fixed by implementing the categorized layout and categorizing number 4 and 5 in a separate display space. Utilizing the composite layout provides a combined view of 2 and 3 to better communicate the relationship between elements. This results in an improved layout shown in Figure B that can effectively communicate information. Moving on to the conclusion, our work investigates the challenges of layout design for MV systems. We propose a transition from user steering to content-aware layout management and provide layout as a type of information synthesis. We believe that these findings can stimulate more research on the importance of layout design in MVs. In the future, we intend to develop more content-driven design layouts to support complex MV systems. That's it from my side. Please let me know if you have any questions. Thank you.
Thank you for the presentation. I have a question from Hyuk. What kinds of influences or effects do you think different layout choices for multiple views have on the relationship between multiple views, such as their design consistency, narrative coherence, and etc.?
Different layout choices on the relationship between multiple views, such as design consistency, matter. The influence that different layout choices can have affects differently through user experiences or the goals that they might have. And the design consistency or the narrative coherence are something that can be taken into consideration when a designer is designing different multiple view systems. So, yeah.
Thank you. So for the sake of time, we'll have to move on, but please hang around Discord. We'll post the questions on there. Thank you again for the presentation. Let's give it a round of applause. And next, we have Maoyuan Sun to talk to us about the systematic considerations of missingness in visual analytics. I also want to congratulate the authors on their Best Paper Honorable Mention Award. Are any of the authors here on site so I can hand out their certificates? Okay, let's just give them a round of applause and we'll figure out the rest.
Hello everyone, this is Maoyuan Sun from Northern Illinois University. I'm very excited to present our recent work towards systematic considerations of missingness in vision analytics. For various reasons such as unexpected system or device failures, interrupted network connections, and intentional information hiding, real-world data is often noisy and incomplete. As a simple example, this data table has a few missing values. Such incomplete data can impact human decisions and may cause severe consequences. Also, to support data-driven decision-making, real-world data is often selected and transformed into various types of visualizations. These visualizations are used for vision analytics, which highlights marrying human cognition with advanced computation for a better sense-making of data by interactive visualizations. However, even with the complete data, a vision analytics-based human sense-making process can still involve missingness, such as biased data selections and partially finished analysis. Thus, the missingness in vision analytics seems more than just the incomplete data. This brings an important question: what is the possible missingness in vision analytics? To achieve a higher quality analytics for making better decisions, it is critical to comprehensively answer this question. As there are two key parties in vision analytics, computation and human cognition, we consider the business in the sense-making process with vision analytics from two aspects, a data-centric aspect and a human-centric aspect. The data-centric aspect regards the information to be analyzed by users, and the human-centric aspect highlights how users perceive the information. Specifically, the data-centric aspect regards business in three data-related categories: data composition, data relation, and data usage. Well, the human-centric aspect considers business in three perception-oriented levels: observed level, inferred level, and ignored level. Now let's talk about each of them in detail. The composition of data has three major components: entity, attributes, and value. There are three possible types of business in data composition, including missing data entities, missing data attributes, and missing data values. Here is an example of such missingness in a data table. Missing data values emphasize the loss of data values, which is often called missing data for short. Moreover, missing data values can be further categorized into three groups: missing completely at random, missing at random, missing not at random. Please refer to our paper for more detailed information on them. In addition to real absent values, missing value has a special case called disguised missing, in which the value is there but not accurate. For example, when answering a questionnaire, a user leaves a default value, such as May 1st for birthday, for privacy concerns. In this case, the value is not missing, but instead a default one that may not match the truth. Missing data attributes refer to the loss of possibly useful data attributes. This may result from an ill-defined problem space that leads to problem in data collection mechanism, or decisions made by considering some practical concerns. For example, when designing a logging system of an application, some user behaviors could be overlooked or intentionally untracked due to an expensive cost. Missing data entities highlight the absence of data entities. It often comes from errors in data collection. For example, in fitness tracking devices, some sensor data might not be recorded due to network connection problems. Data relationship missingness means the absence of relations between data entities. From a graph perspective, it emphasizes the lack of links among nodes in the graph. This means that for a given set of data entities, some connections between them do not, or with a very low probability, exist. The utility of data for sense-making activities involves data selection and analytical method selection, so the data usage missingness can exist in both, such as not a full set of data being analyzed. Observed missingness refers to that user can directly perceive missingness. As the visibility of missingness is affected by the way that data is represented, observed missingness relies on visual context in which data is encoded by certain visualizations. For example, it is easier for a user to see missing links by looking at a matrix than checking the same data displayed as a list of node pairs. Inferred missingness refers to that the visibility of missingness is low or even invisible, so it's impossible for a user to directly observe missingness, but they may infer the possible existence of missingness. For example, reading the given text, one may infer that person 1, 2, and 3 plan to do something together, even though this was not mentioned in the text. Ignored missingness means no observation nor awareness of missingness, and the presence of possible missingness is not considered. This may result from the visibility of missingness is too low to raise user awareness, or due to biases or cognitive determining, user turns a blind eye to possible missingness. However, the ignored missingness may bring critical value for sense-making activity, such as the white space concept in the business domain, which suggests new marketing opportunities. Based on these considerations, visualization may play important roles in handling the missingness. They can be a useful tool to help bridge the gap between the existing and missing data. They can also help to increase the visibility of missingness which may prevent a user from simply ignoring to infer or observe it. We hope this work can draw attention to future studies on visual sense-making with missiness. Finally, we would thank the National Science Foundation, NIU, and U Waterloo for their kind support for this work. I would also thank everyone for your attention, and I'm happy to take your questions.
Thank you, Maoyuan, for the presentation. We have time for one quick question. This is from Vidya Settler. Are there certain layouts and encodings that could be used to effectively communicate the type of missiness and the issues it may have in affecting visual analysis?
Well, first, thanks for the question. I think this is a very good question. So far, based on our the current understanding, I think the most visualization work to review the missing data still use very traditional encoding matrices. I think that's the kind of the state of our things, because reading the empty cells is a pretty common thing. And beyond that, there might be a little bit of work on a graph missing link type of things, but well, unfortunately, there are not much work beyond this existing stuff.
Yeah, there's many questions and space to explore. Thank you again. Let's congratulate the authors on their award. Next, we have David Urich to talk to us about the role of extended reality in surgery. Let's welcome David.
Lab at Duke University. I'm excited to be talking to you about our work using virtual reality to plan for cardiac surgery. Starting off, this is a picture of a radiologist interpreting a pelvic x-ray. It's a fairly old photo, and you can tell because they're looking at the x-ray film itself. If you walk into any hospital today, you're much more likely to see a workstation like this one. Desktop computers have really revolutionized how we use medical imaging and empower doctors to do a lot of really cool stuff. But the point I want to make is that we are still confined to a traditional 2D display. One might wonder if there is another paradigm shift in the making, just like the one we saw with the introduction of desktop workstations. Of course, there is quite a lot of enthusiasm for virtual reality within the medical community. There were just under 3,000 publications in this space last year, and we currently are well on pace to break that threshold. And this makes a lot of sense. Nearly all doctors depend on medical imaging. Surgeons especially need it so they can understand their patient's anatomy before they operate. They also are quite used to using technology in the operating room, so it's no surprise that surgeons are leading the way trying to integrate VR into their practice. One good example of all these challenges is the CABG procedure, or the coronary artery bypass graft. This is a surgical treatment for coronary artery disease, which occurs when the arteries supplying the heart become abnormally narrow or obstructed, preventing the heart from receiving enough blood. The procedure works by taking another blood vessel from elsewhere in the body and using it to carry blood around, that is, to bypass narrowed regions. And as you can imagine, this relies pretty heavily on medical imaging to not only visualize and diagnose the condition, but also to plan for the procedure. For references to the normal coronary artery system, it's usually separated into a right and left side, and each of the main branches has many branches of its own. And as you can see, it can get quite complex. This is a coronary angiogram. It's basically an x-ray of the arterial system. It's what surgeons often use to plan for CABG procedures. And as you can probably guess, it can be quite challenging sometimes to translate these 2D images into a 3D visualization of the arteries. With all this in mind, it might seem intuitive that VR offers advantages over 2D displays for viewing medical imaging. VR is more immersive, but is this immersion actually useful? Well, when we speak about visual immersion and VR, what we really mean is stereoscopy, which is a method of using binocular vision to perceive depth. The advantage of VR is that it can present a different image to each of our eyes, so we can look at a VR chess piece and see it in 3D just like we would in real life, whereas the computer screen on the left can only present one image, thus we lose that information. Of course, several studies have already examined VR's role within surgery. This top one used VR to fit test devices preoperatively, and the bottom two looked at congenital heart disease. And all three of these found that stereoscopy was an essential part of the VR experience. In contrast, some studies have indicated that stereoscopy actually isn't that necessary. This top one here used VR to teach about congenital heart defects, and the bottom one is actually a tool from my lab used to interact with 3D vascular models. So the question we hope to help answer with this study is whether stereoscopic visual immersion actually enhances user performance. Additionally, we wondered whether latent factors such as anatomic complexity might modulate performance between visual conditions. To answer these questions, we first constructed 3D models using catheter angiograms from real patients. We are able to render these models in Harvest, which is a software developed by the Randall's Lab to interact and modify vascular models like this one. We performed the study using the Z-Space augmented reality platform. It uses glasses and motion tracking cameras to enable stereoscopy, and it can also be used without glasses just like a normal 2D monitor. In both cases, users interact using a stylus, and we chose Z-Space specifically because we could use the same input device and display for both conditions, allowing us to isolate the visual condition as the independent variable. This is the Harvest editor. You can see the patient model appearing in white. Users are asked to select an origin and an insertion site for the conduit, which represents the bypass graft. The sliders on the left allow users to adjust the conduit shape, and the jobs on the bottom part of the screen represent previously placed conduits. Here we can see a user using Harvest to inspect one of our patient-derived models. They can zoom in and out, and then they use the stylus to select an origin, and then also an insertion site for the graft, which appears in blue afterwards. Finally, they can use the sliders on the left-hand side to adjust the radius and the arc of the conduit. Overall, we created 3D coronary models from 6 different patients. We had 14 clinicians with advanced training who participated, and we compared the accuracy of their site selections between the 2 visual conditions. To determine accuracy, we used the selections of our most senior participant as the ground truth and treated the distance between their selection and each user's as error. We also wanted to investigate the effect of model complexity, so for each of our patients, we created a second simplified model that only contained some of the branches of the arterial tree. Finally, we also planned to compare between the right and left arterial trees because the right branch is inherently more simple than the left one. Moving on to results, we found that the 2D display had a slightly lower mean distance deviation than the stereoscopic display. However, there were no significant differences between the 2 conditions. Additionally, 13 out of the 14 participants gave equal ratings for both display modes. Moving on to model complexity, for the higher complexity models, the 2D display had both a lower distance deviation and also a more narrow confidence interval. In contrast, both display modes had pretty similar performance for the low complexity models. Finally, when comparing the left and the right branches, it seemed like the stereoscopic condition resulted in greater variability, while the 2D display was pretty consistent. All in all, we found no significant differences between the stereoscopic and the 2D visual conditions. This result challenges the often intuitive assumption that VR displays are better than traditional 2D displays. We will note that it is very important to isolate the visual condition in future studies and minimize the effect of display and input modality. Prior works have theorized that VR's benefit can be affected by task type and objective. This very nice 2014 review classified VR studies by task type, and even found that studies on planning or training tasks, such as ours, see less benefit from VR in comparison to other types of tasks. We'll also mention that physicians' inherent familiarity and comfort using 2D displays could have affected our study. With all that, thank you very much for coming out and listening to my talk. I'm really excited to see this field continue to grow in the coming years, and I hope to one day use VR to view imaging in the hospital. And now I'll do my best to answer any questions you guys have.
Thank you, David, for the great presentation. I have a question for you. How do you think the clinician's level of expertise might influence their interaction patterns in these settings that you're talking about?
Yeah, that's a great question. Part of our study tried to look at experience level. We tried to actually, distinguish between advanced trainees and people who are newer. And we didn't really see a difference. That said, I think, if someone's been practicing for 20 years and does something a certain way, maybe their a little less inclined to try something new. And, we also think that the newer trainees kind of have grown up with this sort of technology, so they might be more comfortable using these new modalities. So I think in future studies, it might be something that you actually see makes a difference. Thanks for the question, though.
Thank you, and I do hope to see the field continuing to grow. We will move on to our next speaker, but let's give David a round of applause before we do. Next, we have Shunango to talk to us about AR shopping. And I want to mention it's such an honor to be chairing this session because this is our other honorable mention paper from this session. Let's congratulate the authors on their award. Please come to me to get your certificate after the session. Thank you.
Thanks everyone for staying in the session for the last paper. And I'm originally very nervous about going over time, but since the entire session is kind of just going over time, so I'm less pressured. Hello everyone, I'm Shinango from Adobe Research. Today I'm very happy to be here and share one of our internship projects that we worked with Bin Jishu from Northwestern University last summer. And this work is also co-mentored by several other colleagues in our lab, including Iniko, Jane Hopswell, Ren Rossi, and Fendu. So I believe shopping is a very important part of everyone's daily life. And with the outbreak of COVID-19 pandemic, people's shopping behavior has actually forced to shift more towards the digital world, where people can actually rely a lot on the comprehensive and precise product information that's usually available online for making the purchasing decision, like the historical customer review and very detailed product specifications. Physical stores, on the other hand, has its own advantage. I believe even during the pandemic, people are still need to go to the physical store time to time because it gives people instant gratification, hands-on understanding of the product. However, people don't usually have access to the product information that they will usually get from online shopping to make the purchase decision. In addition, when shopping in store, people are more exposed to the similar product because they are often just placed right next to each other, which brings even more burden for the in-store customers to make purchase decisions. So with this motivation in mind, in this work, we introduced a web-based prototype to visually communicate detailed product information through augmented reality. So before diving into the details of the technique, I want to first introduce the demo with an example use case. I want everyone to imagine yourself just recently start working out and your personal trainer suggests you to add protein supplements to your diet. So you decide to get some protein bars and stop by the grocery store after training, and here's what you're very likely to see, a shelf of protein bars with all sorts of variety. And with a relatively strict diet plan from your fitness trainer, you want to make sure that the nutrition of the protein bar fits in well with your macro. So you start to check the nutrition facts on each box of the protein bar. However, since there are too many of them, and after taking a look at several of them, you probably will lose track of which one fits best with your diet goal. With the help of AR shopping, however, all you need to do is pull out your phone and put the product you want to compare in front of the camera. And the camera will detect the markers attached to the product labels on the shelf and retrieves the product information for you to explore. For example, you probably don't want to fact too much on your calorie intake, so you can filter products that are high in protein while at the same time have relatively lower calories. You can also filter out products that have bad review, and this will leave you with only 4 options. So you can further compare the nutrition value of the protein bars using the visualization glyphs on the app, which will generate a radar chart that compares the nutrients. So you can also choose which nutrition you want to display in the chart from the drop-down menu. And after taking a glimpse of the visualization, you probably notice that one kind of the protein bar has relatively high in fats and compared to others, so which would probably should be taken out of your option. You can bookmark the rest of the kinds to your collection and enter the product details wheel where 3 bookmark products are and a more comprehensive radar chart will be displayed. So from this view, you can include more dimensions in the radar chart for comparison. For example, different types of vitamins. And after selecting the vitamins, you can see there's actually one type of protein bar that outperforms the other 2, and the purchase decision so far can be made. So you can also take a look at the historical customer review from this page to confirm your decision. So with the help of AR shopping, you can easily get connected to the online product information while you're in store and quickly find the product that meets your desire. So let's now delve a little bit more onto the technical details behind the implementation of the prototype. So at a very high level, our prototype includes two modules: the product detection module that identifies the product in the view of the camera and retrieves the information from the online database. The queried product information is then sent to the user interaction module in the front end to support filtering and visualization. So for the product detection module, here are two problems that we consider when designing the prototype. The first is how can we identify the product in the scene? And the second is how can we get the position and the orientation of the physical product so as we can add the visualization overlay glyph in the virtual scene. So to address these two problems in our implementation, we combine two possible approaches for identifying the product in the scene. So one is the marker detection, which identifies a unique marker on the product label, and the other is a pre-trained object detection model, which is trained with the product image to output a bounding box of the product, while at the same time also identify which type of the product it is. So with the product ID output from both methods, we can solve the first problem by identifying which product is in the scene. However, the object detection is very sensitive to how the product is displayed on the shelf, and it can have a very bad performance when the products are jammed on the shelf, which can happen pretty frequently in the grocery store. And for the marker detection, on the other hand, is very sensitive to the lighting situation in the room. So combining these two methods actually give us a very good chance of mitigating the downside of both methods and enhance the stability of the detection. And the other benefit of combining two detection methods is that it enables the detection of the product position and the orientation for displaying our virtual visualization. So ideally, we will want the visualization to be displayed on the top of the corresponding product in the view for connecting the visualization well with the product, physical product intuitively. So if we only place the visualization with the marker detection, there may be the situation where the position of the marker is not matching well with the physical product in the scene, and also the possibility of the product interfering with each other will bring the overlapped visualization in the virtual scene. So just as shown on the left. And with the bounding box of the product, we are able to resize the visualization to make it cover the right area of the product for people to compare. And in addition to the position of the product, the orientation may also be different depending on where the customer put the camera, so which will result in different distortion of the product in the scene. So to make the virtual object blend well with the physical scene, we want to equally distort the visualization to align well with the physical product. So luckily, with the help of the marker, we're able to identify the orientation of the shelf, which we'll suppose will be the front view. And according to the distortion of the marker, we can equally distort the visualization canvas to create a vivid overlay visualization label for each product. So to assess the usability and the usefulness of our product, for assisting the decision-making during the in-store shopping, we conduct a use case study with 14 participants through online meeting and ask them to try out our prototype with a virtual milk purchasing setting in this picture on the right. So we collect participants' feedback on technology acceptance model, where we can see participants' feedback was pretty positive in all aspects in general. So in terms of the usefulness of our prototype, most participants mentioned the app would increase their confidence of purchase, and also they get to know the product better from our app. And participants also mentioned the value of the product and their familiarity to the product itself would be an important factor of whether they would use our app or not. And in terms of the ease of use of our prototype, participants appreciate that the app is web-based, so that it does not require any additional installation. However, they also raise some concerns on the poor internet connection and the increased complexity of the visualization when adding too much dimension of the to compare. So participants also highlight some features they think it would be helpful for the app to support in the future, including like real-time product recommendation, price trend analysis, and adding narratives to visualization for easier understanding. That's the end of the talk, and I'm happy to take any questions from here.
Thank you for the presentation. I'm going to try to combine the questions by asking, can you share with us some of the design process behind AR shopping, and can you tell us about the rationale for choosing certain visualization representations such as radar charts to represent data?
Mm-hmm. Yeah. So for the design considerations, we are considering for designing the prototype, we actually has an informative study before actually the prototype is developed. So we try to because the initial motivation is to support decision making in the purchase. So we kind of want to know what the customer's consideration when they are comparing the products. So this is the initial consideration for us to develop this prototype. The informative study is actually included in the paper, but it's not included talk for the time consideration. So for the choice of the visualization, actually for the reader chart is probably the most common visualization, because our target user is very novice user who does not really get exposed to much about the data visualization. So reader chart is one of the most commonly used visualization to compare the multivariate data. So consider our case is to compare the product specification. So this is our decision for choosing the reader chart. But there are other charts that can be explored for sure, but consider our target user is very novice user, and even for the reader chart, sometimes they also raise the concern of that may be hard for them to understand, and some narratives may help them better understand the visualization. So yeah, but this can be something to explore in the future.
Thank you, Shunas. Congratulations and the co-authors for the award.
Thank you, everyone.
And that is the end of our session. Thank you all for attending. Thank you for your patience. Let's thank our presenters and our student volunteers for everything. I'll see you around the conference.